In this video, we're going to look at factoring some special cases. And the two special cases we're going to look at are perfect squares and a difference of squares. Now, if we can quickly identify if we have a perfect square trinomial or if we have a difference of squares, we can then immediately factor it into its factored form and save ourselves a whole lot of time and energy trying to use some of the other techniques. So it's sort of, if we can identify it right off the bat that this is a perfect square, we can jump directly to the answer and be done with it. So let's first talk about perfect squares. And if we first identify what is a perfect square, well, let's see, I had x plus 5 squared. This is a perfect square. Well, why is it a perfect square? Well, x plus 5 means x plus 5 times x plus 5. And notice that both brackets contain the exact same term. And if I continue to expand, well, you'll notice that, let's take the first x and multiply those, and we get x squared. We'll take the x and multiply it by 5 and get plus 5x. We'll take this plus 5x, and last but not least, we'll multiply these two and we'll get plus 25. Okay, take a good look at the pattern here. The x times x gave us a perfect square at the front, x squared. The 5 times 5 at the end, well, it gave us a perfect square of 25 as our last term. And then if we focus on the middle for a moment, you'll notice that we've got, well, 5x plus another 5x. We've got two terms that are 5x. And, well, remember, this 25 was actually 5 squared. So where you need to focus is, notice that the first term was a perfect square with x as the base. The last was a perfect square with 5 as the base. And the middle has 5 times x and another 5 times x, two of them. Okay? So we can clearly see that when we combine the like terms, we've got x squared plus 10x plus 25. And this is the pattern that you should be able to look at and recognize, I have a perfect square here, and take this and move directly back and factor it immediately as x plus 5 times x plus 5. Well, how do we do that? Well, here's the steps that you're going to check. First, you're going to look at the first term and you're going to say, is that a perfect square? Yes, it is. Then you're going to look at the last term, and this last term must have a positive value here. And you're looking here to say, is this a perfect square? Yes, it is. So 2 checks so far. Then you look at the middle term. This middle term must be twice, so 2 times, the base that was here, x, the base that was here, 5, because 5 squared, and we're going to multiply that by 2. And that gives us 10x. So this has the perfect square pattern we're looking for. And that pattern is produced, when we look here, x plus 5 times x plus 5 produces 2 of the exact same term in the middle. And it produces a perfect square at the tail end. All right, so let's do a couple of examples. And what I'll do is I'll write a perfect square, and we'll see if we can move directly to the factored answer by recognizing the pattern. So let's try x squared, and we'll say plus 6x plus 9. Well, is that a perfect square? Well, let's just go through our little checklist here. Is the first term a perfect square? Yes, it is. The base is x. Is this a perfect square? Yes, it is. It's positive, which is good. And we've got a positive 9 here, perfect square. The base is 3, because 3 squared gives us 9. Look at this middle term. If I had 3 times x, and then I doubled that, I would get 6x, and that is the middle term. So I can move directly to the factored answer. The two brackets are going to be x plus 3 times x plus 3. And notice that that 3 is what showed up in both of those, and the base of the x showed up in the front of both of them. All right, well, how about this one? Is this a perfect square? Let's say that we've got x squared, I don't know, minus 8x plus 16. Is that a perfect square? Let's go through our checklist. First term, perfect square? Yes, it is. What's the base? The base is x, and it is squared. Last term, perfect square? Yes, it is. The base, 4 squared. Is this positive? Yes, it is. So we're good to go. All right. Well, take a look at this middle term now. Is this middle term, we take the base from here, the base from here, we get 4x. And is that doubled? 8x. Yes, it is. It is 8x. But wait a minute here. It looks like this one has a negative sign, and does that make a difference? Is that a problem? Well, it's not a problem at all, but it does tell us the sign that we need to use inside our two factors. In this case, we're going to have x minus 4 and x minus 4. We still use the two bases in the front and the end, but here we've got two negative values. And notice that if we were to expand this out, negative 4 times negative 4 is equal to positive 16. Okay, so perfect square pattern, if you can identify the pattern, you can quickly move right to the factored form and not have to go through the whole business of finding factors and grouping or a simple trinomial, that sort of stuff. All right, enough of simple trinomials. Let's try, perfect squares. Let's try difference of squares. So first we need to, I guess, identify what is a difference of squares. Well, let's say I had, instead of x plus 3 times x plus 3, let's say it was that. Let's say one of the signs was positive and one was negative. If I was to expand that out, what would it look like? Well, we'd get, again, x times x gives you x squared. Okay. In the middle, I'd get x times 3, or negative 3. I'd have negative 3x. 3 times x, careful, positive 3x. And then to wrap things up, positive 3 times negative 3 is negative 9. Okay, well, a funny thing is going to happen here in the middle, because if I look, in one case I had negative 3x and another positive 3x, and when I add those together, I'm going to get 0. So they're going to vanish. So when I actually write this with the like terms collected, suddenly I only have two terms. So that is the pattern we're going to use to try and identify a difference of squares. That is, if we ever see an expression that has two terms in it, the first thing I should do is I should start thinking this might be a difference of squares. Okay, well, why is it called a difference of squares? Well, take a look at this first term. Is this a perfect square? Yes, it is. The base is x and it's squared. Is this 9 a perfect square? Yes, it is. The base is 3 and it's squared. Well, where's the difference part? The subtraction. There is the difference of these two squares. So if I recognize that pattern, I can immediately move right back up to here and say, I am going to get two brackets. One of them is going to have x minus 3, and the other is going to have x plus 3, because that special pattern will result in the two middle terms vanishing and leave me with just x squared minus 9. So let's see if we can identify that pattern and use our knowledge to quickly factor these. Okay, so here's a question. I have x squared minus 25. Is that a difference of squares? And yes, it is. First term, x squared, perfect square, base of x squared. Second term, perfect square, base of 5 squared. There's only two terms, and they are joined by subtraction. So they must have come from x plus 5 multiplied by x minus 5. Difference of squares. Let's try one that's a little harder. What about 4x to the fourth minus 1? Is that a difference of squares? Well, what should immediately make me think this might be a difference of squares is the fact that there are only two terms and they're joined by a negative sign or subtraction. I'm not overly concerned that this is a x to the fourth power and the other one was an x squared. That's not on my radar at all. Just the fact that there are two terms and they are joined by subtraction, I'm going to go down the road of, I wonder if this is a difference of squares. So the first thing I'm going to do is I'm going to look at this and say, is this a perfect square? And it is. How's that a perfect square? Well, look, 2x squared squared gives me 4x to the fourth. So the base is actually 2x squared. This 1, is that a perfect square? Yes, it is. What is it? Well, it's 1 as the base, and it is squared. So that means that I can immediately go to the answer of, I've got bracket 2x squared plus 1 times 2x squared minus 1. Okay? Now, you might think, well, wait a minute here. Have I created another difference of squares in this second bracket? Should I keep going? And it looks promising, but if I look at this first term here, I cannot create a perfect square out of that. Okay? But try this one to wrap up. What about just plain old x to the fourth minus 1? Is that a difference of squares? And it is. If I look at the first term, perfect square, yes. What is it? Well, it's x squared squared. The base is x squared. 1? Yep. 1 squared. So that means that this will factor into x squared plus 1 and x squared minus 1. Well, that's really good. So I guess I'm done. And here's where you always have to be careful. Check to make sure you have not created another difference of squares. All right. Using our pattern, x squared plus 1, and I know that this x squared minus 1 is going to factor into x plus 1. Notice the squared's gone. And x minus 1. Now we're done. Okay? So, two patterns you need to recognize. A perfect square, easily recognizable because of the perfect square at the front, the perfect square at the end, that's positive, and then you look at that middle term to see if it's twice the multiplication of the two bases. Difference of squares, well, your radar should start beeping if you see two terms joined by subtraction. Then you can start investigating and say, is the first one a perfect square? Yes. The second one, is that a perfect square? Yes. And then you know that, that you have a difference of squares here. Okay? All right.